Okay. All right, so this is the last lecture on the diode chapter, and this is going to be covering metal semiconductor junctions. So throughout the diode module, we've been learning everything, all the aspects of p-n junctions, when you take a p-type material and an n-type material, and you put those two together. You know, we talked about the depletion region, what happens in forward bias, what happens in reverse bias. But now we're going to talk about something that happens when you take a metal and a semiconductor and you put that together. So in order to do that, we're going to understand the band diagrams of a metal. And then we're going to take a metal band diagram and a semiconductor band diagram and put them together. And we're going to see that sometimes, depending on what type of metal you have and what type of semiconductor you have, sometimes you'll form an ohmic contact and sometimes you'll form a diode. Okay, so that's going to be the objective of today. I'm hoping it won't take terribly long. There's only 15 slides on this. Okay, so first of all, why are metal semiconductor junctions important? Well, you have the simple problem of whenever you have a semiconductor, let's say you just have a p-type semiconductor, this. The p-type semiconductor. Okay, a p-type semiconductor is going to act as a resistor. You need to make metal contacts to it. All right, so if you actually want to use the semiconductor in a circuit, you have to attach wires to it. And the way these wires are attached are through metal pads, or what's called contact pads. And I actually realized I should have a picture of this. So let's just do a quick Google search on this. IC contact. Well, here, nah, that's not what I'm looking for. Hold on, one second. All right, well, let's see. I guess this is one picture that we can kind of work with here. So this is an actual picture of a typical semiconductor chip. You know, this has all the transistors inside of here. You'll notice around the edge of the semiconductor, you have these metal squares, right where I'm pointing at here. Okay, these are called metal contact pads. This is how you make electrical connection to the semiconductor. And the way contact is usually made is you have the die, which is a very small chip, only usually a few millimeters by a few millimeters. And then you have these electric contact pads all around the outside. And sometimes they're arranged in a two-dimensional grid. A lot of the modern semiconductor dies have that. And then there's these little wires that connect these little contact pads to a larger contact pad. And these larger contact pads are the ones that are then connected to your printed circuit board. Okay. So, I mean, the details of this is not all that important. I think the main point I want to get across is that you have a semiconductor and ultimately you have to connect a wire to it to connect it into your circuit. So, you know, you have to have one second, I'm having some technical difficulties here. I'm going to close my extra windows here. All right, let's try this again. Looks like my pen is not working. So sorry about this. So you have a metal, you have a semiconductor, and you have to basically make a metal contact to that semiconductor. Okay, so in some cases, that metal contact will form something called a Schottky Barrier diode, which has diode-like properties. And in some cases, that metal junction will form an ohmic contact. An ohmic contact is looks more like a resistor, like it has a small contact resistance associated with it, but it doesn't have any weird properties like a diode where current will only flow in one direction. Okay, so as one example, a lot of times when we want to just make a metal contact into a semiconductor, we would like to have an ohmic contact so that current can flow in both directions. In other cases, we may intentionally form a Schottky barrier diode if we want the current to only flow in one direction. All right, so let's just start by understanding the energy band diagram of metals. We'll go over that a second time, and then we'll go over the energy band diagram for semiconductors and then put them together. So this is a reminder from Module 2. What is the work function of a metal? Okay, the work function is going to be important in creating the energy band diagram. So suppose a metal or semiconductor is bombarded with energy. If enough energy is supplied, an electron is released from the material, and this is called the photoelectric effect. This is what Einstein discovered, and his experiment was to take a piece of metal in vacuum and you bombard it with energy. The type of energy that he used was just light. Okay, E is equal to H times the frequency here, which is E equals HC over lambda. Okay, so depending on the wavelength of light that you use, you can determine an energy. So in his experiment, he started off with low energy light. Okay, and with low energy light, the electrons are excited to higher energy states, but not high enough that the electron actually has energy to escape the material. Okay, so then he increases the energy of the light by reducing the wavelength, and eventually he gets to the point where electrons are being ejected off the material, and that is the photoelectric effect. And these electrons that are ejected can be detected with something called a Faraday cup or other types of electron detectors. Basically, it creates small blips of current when the electrons hit it. So we won't go into the details of that. But the point is, when the energy is high enough, when the electrons absorb a certain amount of energy, they have enough energy to escape the atomic lattice completely. And that energy is called the work function. Okay, so the work function can apply to metals. So you can call that phi sub m, the work function for a metal. And you can also have a work function for a semiconductor, phi sub s. And this is just a reminder of what Einstein's experiment was. As the frequency of the light increased, he was measuring the energy of the ejected electrons. So at this point here, he saw no electrons, so the energy was zero. Once he got to a certain minimum energy, which is what he defined as the work function, then the electrons started to come off. And as he increased the energy further, the energy of the ejected electrons increased. So they had more kinetic energy, and that's something that could be measured with the system. So this is how the work function of a metal can be measured. All right, so let's talk about the energy band model of the work function. So we've already said that if enough energy is provided to an electron, it can go to an energy state which represents the energy of an ionized electron. So let's see what that looks like. So with energy band diagrams, of course, we have energy on the y-axis. And then remember what we said with metals, is that metals have this a band, okay, just like semiconductors have different energy bands. That's where a lot of energy states are clustered close together. But the difference between a metal and a semiconductor is that in a metal, the Fermi level actually appears within the band, So just as a rule of thumb, remember below the Fermi level, it's mostly filled. and above the Fermi level is mostly empty. Okay, so what this means is that this band has a lot of carriers down here, and it also has a lot of empty states, both within the same band. That means these carriers can move around very easily within the band because there's so many empty states that it can move around in. So that's why metals are very good conductors, because they have lots of carriers and lots of empty states. So we know about the valence and conduction band in a metal, but a metal just has a single band. So this energy band model for a metal looks a lot simpler. So the metal has another energy state called E sub 0. And this E sub 0 is called the free electron level. Okay, this is an energy that represents an electron that's free from the lattice. It is ejected from the material completely. All right, so the work function is simply the distance between the Fermi level and E sub 0. Because remember, most of the electrons are just below the Fermi level, or below the Fermi level here, okay? So just as a way to define where, what energy a lot of the electrons are at, they would be at or below the Fermi level. So we just use the Fermi level as a reference. An electron has to absorb Q phi m's worth of energy to get to the E sub 0 state. Okay, and that is the work function. This notation, Q times phi m is a quantity given in volts. It's given in volts, and then this Q phi m is converts the volts into electron volts. Okay, so in an energy band diagram, this distance is going to be Q times phi m. And then in the real world, if you were to actually have phi m and you're measuring diodes built with metals, this difference in energy corresponds in the real world to a voltage, phi m, represented by the metal work function. We'll get into that in just a second. So if that confuses you, just bear with me for a minute. Okay. Now, for a semiconductor, our band diagrams, we have our conduction band, valence band, the Fermi level here. Then we have EV and EC. Okay, remember the conduction band, the band of energies resides above EC, and the valence band resides below EV. The valence band is mostly full of electrons, and those electrons are the ones that are participating in covalent bonds. And then the conduction band are electrons that are in a loosely bound state. So they are kind of represent electrons that are free to move about the lattice. Okay, the conduction band is typically mostly empty. Valence band is mostly full. Okay. And remember, the last concept is this Fermi level can move up and down depending on doping. It'll move upwards. If you dope it N-type, the Fermi level moves towards the conduction band. If you dope it P-type, the Fermi level moves towards the valence band. Okay, so in the semiconductor, you also have E sub 0, which represents the free electron level. Even in a semiconductor, if you bombard an electron with enough energy, that electron can go all the way up into the at the free electron state, meaning it's not just loosely bound to the lattice. An electron that's in the conduction band is loosely bound to the lattice. It can move around, but only within the lattice. Okay, if you go to even higher energy, E sub 0, then the electron has enough energy to escape the material completely. So in a semiconductor, you have a semiconductor work function, which is defined as the difference in E sub 0 and E sub f, Fermi level. So you have the semiconductor work function. And then in semiconductors, there's also something called the electron affinity, which is given by Q times this Greek letter. And that represents the energy required for an electron that's in the conduction band to go up into the free electron state. Okay, so just two different quantities we have to think about. Now, the reason why this factor is here, the electron affinity is here, because The electron affinity is not doping dependent. This is a constant, and it's 4.05 electron volts for silicon. Okay, this quantity here. Phi s, on the other hand, as I mentioned, the Fermi level can move up or down depending on doping. So Q phi s is going to depend on the doping. Okay. Again, comparing to a metal, phi m for a typical metal, the work function is fixed. Gold will have a certain work function. Copper will have a certain work function, and so on. All right, so let's go to the first type of metal semiconductor junction. You combine your metal with an N-type semiconductor. This is the first example. Okay. This is a case where the metal work function phi m is greater than the semiconductor work function phi s. We are going to be going over the other permutations and possibilities of phi m and phi s as we go along in this class. We're just doing this first one as an example. So a spoiler is that this is going to form what's called a Schottky Barrier diode, which has diode-like properties. And we're going to understand why by drawing the energy band diagram. So the way we'll draw the energy band diagram is very similar to how we drew the band diagram for a diode. Okay, the first thing you do is you draw the semiconductor and the positioning of EC, EV, EI, E0, and the Fermi level, EF. That's not written here. You can just add that. Of course, it depends on the doping and the band gap of the semiconductor. So you already know how to draw a semiconductor band diagram, so we won't belabor that point much. The thing that we are adding is this guy here, okay? To our semiconductor band diagram, we are going to add E sub 0, which represents the free electron level. And that will be placed at a distance Q phi s above the Fermi level. Okay, or if you want to use the electron affinity, it can be placed Q times X above above EC. So the distance between EC and E0 will be 4.05 electron volts. All right. So one little subtle point I want to make here is that if you're given the semiconductor work function, you should actually, if you're given the semiconductor work function and you're given the electron affinity, then you should be able to calculate where the Fermi level is located. And based on where the Fermi level is located, you should be able to back calculate what the doping is. Okay. So the next step is you're going to draw the metal. So the first thing you want to do in the metal is you want to line up EF and then add E0 in there. Okay. So remember at equilibrium, the Fermi level is a flat horizontal line. There's no change in the Fermi level from one side to the other. This is with 0 volts applied. The metal is going to have a certain work function associated with it, and we're going to kind of line up the band diagrams. The Fermi level is the anchor that lines up the two sides of the band diagram. In this case, phi m is greater than phi s. So when we draw out the metal work function, we have to draw phi m as being larger than phi s. So that's why our E0 is way up here, whereas with the semiconductor, it's a little bit lower. All right, so that's step 2. Now, step 3 is we have to connect the band diagrams together just like we did with the diode. In the case of the diode, we connected the conduction bands, EC. We also connected the valence band, EV. But a metal doesn't have EC and EV. So in this case, we will connect the free electron levels, E0. Okay, the free electron in the metal has to be continuous with the free electron level in the semiconductor. Just like the conduction bands had to be continuous in a diode. Valence band had to be continuous in a diode. Okay, so our band bending is actually going to arise from bringing these two free electron bands together. And it's going to look like this. Okay, show you again. it curves up like this, okay? So this side is smooth, and this side is sort of an abrupt. Okay. So what does this mean? This means this negative slope here means that there's an electric field. Okay, the electric field is proportional to the slope of the band diagram. So that means it has a negative electric field, and that negative electric field means that the electric field is oriented from right to left. So from N to P. So we can assume here that the electric field is going to go in this direction because you have a negative slope in the band diagram. Okay, now just a little bit more of a detail here. You'll notice that E0 is flat like this. Okay, that means there's no electric field in the metal. Okay, in a metal, one of the properties of metals, which if you've taken a class in electromagnetics, you might know this, but metals, inside the metal, there can be no electric field. There can be charge on the surface of a metal, but there can't be any electric field inside the metal. Okay, that just has to do with the nature of how metals are. They'll actually spread all the charges to the surface such that there's no electric field inside of it. So in a metal, the electric field stays flat like this. As soon as you get into the semiconductor, you can have an electric field in there. And the electric field, guess what that is? Guess where the electric field comes from in a semiconductor? The hint is it's identical to a diode. Can anyone guess what this region might be?
Depletion region.
The depletion region, yeah, exactly. So that's kind of interesting that we learned about forming depletion regions with a p-type semiconductor and an n-type semiconductor. Now I'm telling you that, well, a depletion region can also form with a metal and an n-type semiconductor. So you're probably scratching your heads and wondering, like, well, what are the physics of the depletion region? How does it form when you don't have two semiconductors together? So that's what we'll go over next. But just to, before we get into the details of that, just to finish up this diagram, there is a depletion region here. There's an electric field. And just like a PN junction, at some point, the depletion region ends and your electric field is just horizontal again, like this. And that is referred to as a neutral region. Okay, so now, again, we're going to get into the physics of the depletion region in just a second, but let's analyze what's happening from an energy band diagram standpoint. So the process that we use in energy band diagrams, remember, first we draw the band diagram by lining up the Fermi levels and then bending the bands accordingly. The second thing we do with energy band diagrams is that we think about what the carriers are doing. Where are the carriers and what are they doing? Okay. So we have to think about a couple things here. In the semiconductor, we have an N-type semiconductor, okay? So that means we have lots of electrons. We don't have very many holes, so we're not really too concerned yet with what the holes are doing, okay? We do have electrons. The electrons in the N-type semiconductor, they can go, remember, electrons can go back and they can go horizontally in a band diagram. They also like to go to lower energy states, okay? So imagine that we have these electrons here. The electrons, can they move into the metal? Well, not really, because you have this potential barrier, okay? So just like a diode at equilibrium, these electrons experience an energy barrier, okay? That prevents electrons from flowing from the N side, from diffusing from the N side, or moving in any way from the N-type semiconductor into the metal. So this is blocking the current here. And then, so you have a built-in potential here that's QV0. On the other side, you have a barrier height here, okay? Can anyone tell me where the electrons are going to be in the metal? The electrons will be below the Fermi level. Okay, most of the electrons occupy energy states below here. There may be some above the Fermi level as well, but most of the electrons are below, like this. Okay, so the electrons on this side of the junction, they have a barrier as well, and that barrier prevents the electrons from going from left to right. Okay, so so it looks like this device of combining a metal and an N-type semiconductor forms a barrier. Okay, and that barrier will block the flow of current, just like a diode does. Okay, but as we're going to see, that if you apply a voltage to it, you can actually reduce this potential barrier, just like a diode, and allow current to flow. So we'll get to that in a second. So the built-in potential in this case, the formula for the built-in potential is different than that of a diode. It is actually equal to phi m minus phi s. And you can just look at the band diagram and tell right away. This is phi m, so this line here is phi m. This line here is phi s. Okay, and if you look at the difference between the two, that will be your V0. That'll be your difference in potential. Okay, because this tells you the difference in phi m and phi s tells you how much this line bends up here. Okay, I think that's the easiest thing to see. Here's phi m, here's phi s. The difference between the two, this distance here, is how much bending you have in the E0. And the EC bends by the same amount. Okay, so that's your built-in potential. The barrier height is given by phi m minus the electron affinity. And remember, the electron affinity is the distance between EC and E sub 0. Okay, so we have two barriers here. So now let's look at the physical model to sort of fill in our heads like what's happening on the, what's happening to the carriers, what's happening on the physical side of things. All right, so some of the key points is that in a metal, charges only accumulate on the surface. All right, so the story goes like this. Electrons will diffuse from the semiconductor into the surface of the metal and accumulate there. Okay, the electrons diffuse from the N-type to the metal, just like they do in a p-n junction. But the difference is that they won't go into the metal. They'll accumulate on the surface of the metal. Okay. So, of course, when the electrons leave the N-type semiconductor, it leaves behind a space charge region or a depletion region. Okay, so these red circles that you see here are the classic N-type depletion region. They are like phosphorus ions, dopant ions with a +1 charge. Okay. Now, the difference here is on the other side, you don't actually have a depletion region on the other side. You just have a buildup of negative charge. Okay, which is kind of interesting. You have a buildup of negative charge on the surface of the metal. You don't actually have a depletion region because you don't have dopants in the metal. All right. So, so this charge distribution and the electric fields in this junction actually represent, in some ways, it's similar to a P plus N junction. In a P plus N junction, remember that virtually all of the depletion width was on the lighter dope side. Okay, so think about in the extreme case where you had a P plus, something that's doped very, 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 very high. So it acts like a metal. If you dope a semiconductor at a very high doping density, it's going to behave like a metal. Okay, and if you think about just increasing, then the depletion region on the P side of the junction is going to get smaller and smaller and smaller. And this is, you can think about this as being the extreme case of that, where there's virtually zero depletion width on this side. Okay, so there's really no depletion region at all on the metal side, and there's only a depletion region on the semiconductor side. You just have a thin layer of charge, and these are negative charges. They're electrons. Okay, any questions so far on the formation of the depletion region in a Schottky barrier? Okay, all right. So just again, I want to reiterate one point, is that in a traditional diode, electrons diffuse over to the other side and then they recombine. In this case, electrons are diffusing over to this side and they accumulate, forming a charged surface. So you have mobile charges on this side, immobile charges on this side of the depletion region. Okay. But a lot of other aspects are the same. You have a width of the depletion region. Okay. Remember how I talked about it at the beginning of class today, that for a one-sided junction, a P plus N junction, for example, the properties, the physical width of the depletion region is determined by the lighter doped side. And this is an example of that, actually. All the properties of this Schottky barrier diode are determined by the doping on the N-type semiconductor, like the depletion width, for example. Okay, and in fact, you can use the formulas for a P plus N junction to determine the depletion width for an N-type Schottky barrier. All right, so this is this slide shows the Schottky barrier in the forward and reverse bias. Okay, forward bias and reverse bias is similar to a diode. So let's look at what happens here. Forward bias decreases the barrier and increases the diffusion of electrons to the metal side. Okay, so I already showed you the diagram for the device at equilibrium. So now if you look at the device at forward bias, what's happening is that forward bias, the right side of the band diagram is moving up. All right, so this is your metal, this is your semiconductor. Okay, you are applying a positive voltage on this side, and the negative potential is going on the other side. Remember, in energy band diagrams, whichever side has a negative potential, this side has the higher Fermi level. Okay, so you have the Fermi level on the semiconductor side, and then the Fermi level on the metal side. And these are separated by a distance equal to Q times the applied voltage, V. Okay, and you can see here that by applying this voltage, you're reducing the barrier height. You're reducing the curvature of that band diagram. You're reducing the band bending. So this is, which was originally Q V0, now becomes Q times V0 minus V. So just like the diode in forward bias, the barrier height, the potential barrier has been reduced by an amount equal to V. All right. So what do you think will happen if we reduce that barrier height?
More electrons will diffuse.
Exactly, yeah. So if I draw my electrons as dark circles here,
This shaded in kind of L here, is this like just showing that it's a metal and not?
Ah, yeah, good question. I'll get to that in a second. So the electrons now, enough higher energy electrons can diffuse over this potential barrier and get onto the metal side. And once the electrons are in a metal, remember, electrons can flow very easily through a metal. It's a conductor. Okay, so they will go over to this side. They'll find energy states in this region, and they will be able to continue on like that. Now, Melvin, your question was, what is these gray regions? So below the Fermi level, there is there are a lot of electrons. You remember, most of the energy states are full below the Fermi level. So it's just a reminder that these energy states are full of electrons. Does that make sense?
Yes, it does. Thank you.
Okay, great.
Is there a possibility in these cases to have any sort of like Zener breakdown?
Oh, that's a really good question. Well, the basic definition of Zener breakdown, you'd have to have the conduction band. You'd have to have the valence band on the p side of the junction crossing or going above the conduction band on the n side of the junction. You know, if you had a situation like when we get to reverse bias, well, let me hold off on that a second until we get to reverse bias, Corey, but that's a good question. I think it could happen, but it's not something that's that usually jumps out in textbooks. But let's finish up with the forward bias. We'll get to this in a second. So how about, what is different? How is this different from a diode? So we see there's something similar, that the electrons are moving over the barrier. They're moving over to the other side. So what's different? Maybe we can look at what the holes are doing.
So in this case, I assume that there wouldn't be any holes, right? At least not in the metal.
Yeah. In the n-type semiconductor, there's very few holes, right? Because the Fermi level is well above the valence band. That means below EV is mostly full of electrons. And then in the metal, this is also mostly full of electrons. So there's not really much interesting stuff happening with the holes. The electrons are the ones that are doing most of the interesting work in an n-type Schottky barrier. Okay, so that's a key difference. How about the reverse bias? When we reverse bias, just like a diode, this is where your, this is obviously self-explanatory at this point, but just drawing it anyways. This is where the semiconductor side has a positive potential and the metal has the negative potential. So the semiconductor side has a lower Fermi level. So you have your lower Fermi level here, EFS, EFM. Okay, the distance between these lines is not quite shown in this diagram here, but this is equal to QVR, this distance here. Okay, and that results in band bending. It increases the band bending to Q times V0 plus VR. So the bending increases. Okay, and this starts to look very much like a reverse bias diode. You have your electrons here like this. But even the high energy electrons don't have enough energy to get over the potential barrier. Now, Corey, to your question, if you look at like what happens in Zener breakdown in a semiconductor, you have electrons, high energy electrons. Let's say we draw an electron like this, and the electron obviously sees a potential barrier. It cannot do this. It cannot go over that potential barrier. But if the potential barrier is super thin, if the potential barrier were super thin, then an electron could potentially tunnel across like this, and then it'll find lower and lower energy states and get over to the other side. So according to the energy band diagram, the mechanism should be possible in a metal semiconductor junction. So you can look up, if you're curious, I mean, you can look up whether Zener breakdown happens in a metal semiconductor junction. Okay, but the mechanism should still be possible.
Mm-hmm. Okay.
That's actually pretty interesting. Is it possible that, given how we were saying that when you apply a light, it ejects an electron from the metal. If the light has enough energy, if you apply an electric field high enough to the metal, or low enough, or reverse bias enough, could it possibly eject an electron from the metal, which will kind of tunnel over? I guess that's interesting.
I don't know if you are you saying just by applying a voltage, or would you also be applying some kind of light stimulation to energize the electrode?
Just by applying a voltage.
So just by applying a voltage, this electron here, like it could go across in energy like this. By applying a voltage, what you're doing is you're changing the Fermi levels on the two sides. Okay. Only by adding energy to the system through like an optical stimulation, for example, could you get an electron to just go to a higher energy state, which to go up like this and possibly be ionized. But in this case, like what's happening is you're changing the Fermi level on this side. So if your electric field is so strong that and that would decrease the width of this depletion region, then an electron could potentially tunnel through like this. But the mechanism that we're thinking about in terms of ionization, where the electron goes up to E0, that's a different question, I guess. I suppose if you applied such a huge potential that E0, if E0 appeared here on the diagram, if you applied a very, very large potential such that the E0 state was actually below the Fermi level of the metal, maybe.
I see.
Yeah. So, okay. Hopefully that addressed your question. Any other questions? Okay, so let's continue then. Okay, this is the Schottky barrier IV curve. So it behaves very much like a diode, and it does follow the ideal diode equation. So I equals I0 e to the QV over KT minus 1. The difference is that this I0, remember for diodes that I0 involved electrons and holes. There are two parts of that equation, and there was a certain way that was derived. We went over that. But in a Schottky barrier, it turns out this I0 is proportional to the exponential of the barrier height. So it's derived in a different way. We're not going to be talking about how that's done in this class. It's non-trivial. But just to know, just so you know that it is an exponential function of the barrier height. Okay, again, the barrier height is this distance here in the band diagram. Okay, and that barrier height is phi m minus x, the electron affinity. Okay, so you know, I would, if I gave you a question on the Schottky barrier diode, I would give you, I'd probably give you the saturation current I0. Then you can calculate the current using this ideal diode equation. So now let's look at the p-type Schottky barrier. Okay, so to make a p-type Schottky barrier, you have to have phi s is greater than phi m, and you have to have a p-type semiconductor. Okay, and so I just grabbed the diagrams from the book here. There's two diagrams that we can draw. Okay, the first diagram is where you line up the E sub 0. Okay, that's what this blue line is here. So this is E sub 0 for the metal, and this is E sub 0 for the semiconductor. So we line them up at the beginning, just so you can see from this diagram that phi m is less than phi s. Okay, so this distance here is less than the distance, the semiconductor work function in the semiconductor. All right. So at equilibrium, the Fermi levels have to line up. So this one and this one here, they have to line up. So you imagine the right side of the diagram is moving up. The entire right side of the diagram moves up until the Fermi levels line up. That's the way that you want to kind of picture that animation in your head. Okay. So when the Fermi levels do line up, the E zeros, if I draw the E zeros up here, it'll look like this. E0 for the semiconductor will be higher than the E0 in the metal. And so there will be some band bending that goes down like this. Okay. And so the conduction band and the valence band also bend by exactly the same amount, because the distance between EC, EV, and E0, that has to stay the same everywhere in the semiconductor. Okay, so I'm just going to erase that E0 so it's less clutter on the slide. That's where the bending came from. So now you have a barrier here instead of here, okay? So why is that? Let's think about this for a second. In a p-type semiconductor, there aren't many holes up here. There aren't many electrons up here because this is p-type. EF is way down here, so there are very few electrons up here. Okay, so not much is going on in this region here. Instead, since it's a p-type semiconductor, we turn our attention to what the holes are doing. So we look on the valence band. Okay. In the valence band, there may be a region just below the valence band which has some holes in it. I think that's what's represented by this light shaded area. Okay, so there can be some holes in the semiconductor, and those holes would be able to diffuse over to this side, but they cannot because there's a barrier height. There's a barrier there. Okay. And that barrier height is equal to Q times phi s minus phi m, just the same as it was with the n-type Schottky barrier. And so this is your built-in potential here. And in this case, it has diode-like properties. It has a depletion region. There's a positive buildup of charge at the surface of the metal. And then there's a negative depletion region in the semiconductor. Okay, so it's just like the converse of what we looked at with the n-type barrier. And this behaves similar to an N plus P diode. You can apply the same similar equations, this ideal diode equation. You can determine the width of the depletion region on the P side, and so on. Okay. One more point I want to mention. I mean, this is, it follows exactly the same type of approach as for the N-type. When you forward bias the P-type Schottky barrier, this barrier height goes down. So you will on this side of the diagram to go up, and this side of the diagram to go down. So you actually need to apply a positive potential on the P side of the junction in order to make this go down and reduce the barrier height. Okay, so forward bias for a P-type Schottky barrier means you are applying a positive potential to the P side. Any questions? All right, so now let's talk about ohmic junctions. So we've covered two types, right? We've covered the N-type Schottky barrier, where you have a metal and an N-type semiconductor, phi m is greater than phi s. Then we talked about a P-type Schottky barrier, where you have a metal and a P-type where phi m is less than phi s. So there's two other combinations that we have to consider. And those are the ohmic junctions. So ohmic junctions are metal semiconductor junctions that are designed to operate like a resistor and have a linear IV characteristic rather than a diode-like characteristic. All right, so this is what an IV characteristic looks like for a diode. We've seen that before, obviously. Small negative current and an exponential increase in current when you're at forward bias. With an ohmic junction, there's a linear IV characteristic. Between the metal and the semiconductor. Okay, these are two lines shown. I could just draw one line that represents a linear characteristic, but I drew two lines here. And the question I want to ask you is, which one is a better ohmic junction? And think about why, what would make a better ohmic junction from an engineering or circuit design standpoint. You want to make good contact into the semiconductor. Which of these curves? Let's say this is A, and then this is B. So I'll just put A and B here. Oops. A and B. Which one is a better ohmic junction?
So if we're trying to interface with the outside world, so we want to kind of ideally, the ohmic junction would be some horizontal line or just minimum resistance.
Minimum resistance, that's correct.
So
you got it, minimum resistance. But it's not going to be a horizontal line though.
right, it'll be, I would think that B is probably better since it's lower resistance.
Well, take another look at this plot. It's I versus V, not V versus I.
Yeah, A is
yeah,
better.
that's always a thing that believe me, I do the same thing. So this is I versus V. Like if in this case, remember Ohm's law, V equals IR, and this is Y. So this I in terms of V is going to be 1 over R times V. Okay. So in this plot here, the slope is the inverse of the resistance. Okay. So you want to have something that has a smaller slope. I'm sorry, you want something that has a large slope so that it has a small resistance. Okay, for those of you who aren't from a circuit design background, whenever we design circuits and we're trying to make a nice contact into a material or something like that, we don't want to have resistances. We'd like to have the resistance to be where we design the resistance to be. If we're just trying to make a contact into the semiconductor, we usually want the resistance to be as little as possible. So this line here, A, has a larger slope. Larger slope means smaller resistance. Another way to think about it is that if you look at V equals IR, you want the ohmic junction to be able to support a lot of current I with only a small voltage V. So then that's another intuitive way you can look at this plot. Okay, so A would be the better ohmic junction because it has less resistance. So if we want to make an ohmic junction in a semiconductor, there's two ways to do it. Number one, we can choose the work functions that are opposite the Schottky type, or we can dope the semiconductor side very high so we get tunneling. And those are the two mechanisms that we're going to be talking about now. Okay, choosing the work functions appropriately. So phi m is less than phi s for an n-type. Phi s is less than phi m is less than phi s for an n-type. Phi s is less than phi m for a p-type. So we'll go over those two right now. So an n-type ohmic junction. So we have a metal and an n-type material. Oh, there's my laser pointer. Phi m is less than phi s. If phi m is greater than phi s in a metal n-type, then you'll get a Schottky barrier. Okay, so let's look at the band diagram for this. So the first thing you can do when you're drawing your band diagrams is you can draw the metal side. You draw the semiconductor side. If you want, you can start by drawing, by lining up the E zeros, or you can go directly to the, the equilibrium band diagram, which is shown on the right. So here you can see that phi m is less than phi s. Okay. So again, we imagine the right side of the diagram moving up, so that these Fermi levels line up at equilibrium. And as this right side of the diagram moves up, that means E0 in the semiconductor has to bend down. So that's why you see this. So I'm looking at the right side of the diagram right now. You can see that this is bending down. Okay. This is not labeled here, but this is obviously the conduction band, and this is the valence band. Okay. So we have, now that we've drawn the band diagram, we have the band bending happening here. Now we got to look at what's going on. Fermi level is here. It's close to the conduction band. So we're obviously going to have electrons. Okay, but the difference here is that the electrons don't see any kind of barrier height. So the electrons can easily move over to the metal side. And once they're in the metal, metals conduct. So there's no issue once it gets over to the metal side. Similarly, the electrons can actually go the other way too, because this, you can see here that there is a barrier, but that barrier is very small now. Before, that barrier was much larger. Okay, if you have a small enough barrier, that means that even a small voltage, even with a small applied voltage, you can have carriers moving back and forth. In this case, the electrons. So this type of device, it supports current going in either direction. It does not have diode-like properties. Okay. So in an n-type ohmic junction, the holes aren't really doing all that much. There's very few, there's very few holes in an n-type semiconductor. So most of the interesting thing is the thing that we want to pay attention to is happening with the electrons here. And finally, let's talk about the p-type ohmic junction. This is when you have a metal and a p-type semiconductor with phi s is less than phi m. Again, you draw your the metal and then the semiconductor. You have your E sub 0 here, the E sub 0 here. You notice that the phi m is greater than phi s. So when you line up the EF and ES together, you're going to get band bending that now looks like this. It goes in the opposite direction here. Okay. So now we have a p-type semiconductor. So we have holes. There are a lot of holes here. And these holes now They do not see any kind of barrier to go back and forth. So these holes are able to go back and forth in the semiconductor depending on what type of voltage is applied. Okay, and again, this barrier height here is quite small, so it can be easily overcome with even a small applied potential. So this conducts current in both directions, and the current is due to the holes instead of the electrons. Questions? All right. There's one more type of ohmic junction I'd like to cover, and that is the tunneling type ohmic junction. Okay. And this is it's, Corey was asking a question about tunneling in metal semiconductor junctions earlier when we were talking about the behavior in reverse bias. But tunneling does happen, and you can actually take advantage of tunneling to get a nice current flow even when you're not in reverse bias. Okay, and this is how it works. So this example here is a metal, so the example, this is a metal N-type material, okay? If the metal N-type doping, if you have the standard Schottky barrier with moderate doping in the semiconductor, then your band diagram is going to look like this, okay? This is the same band diagram we went over with the metal N-type Schottky barrier. This presents a barrier to electron flow. So unless you apply a potential, that barrier will not be overcome. So you'll only get current flow in one direction. But if you take the same N-type material and you make the doping very high, then you still have a potential barrier, but that potential barrier is very thin, meaning this width, the width of the depletion region is very narrow. If you have a very narrow depletion region, as we saw before with Zener breakdown, you can have an effect called tunneling. Tunneling is where instead of the electron going over the potential barrier, it can tunnel right through it. The probability of tunneling increases exponentially as the width becomes smaller. So if you take an N-type material and you want to, you have a metal and N-type junction, and you will just want to ensure that regardless of the metal work function, you get an ohmic junction. This is one way to do it. You just dope the material very, very high. Okay, now I'm going to draw out what I mean by this, okay? So let's say I have an N-type semiconductor like this, and I want to make a metal contact to it. So I can put a metal contact pad on top of it, and this can be connected to my electrical circuit. Okay, so I have one contact into the semiconductor like this. If I make this contact with a metal, great. I have a metal semiconductor junction. Now, in this case, obviously, whether this junction is a Schottky barrier or an ohmic junction depends on the work function of the metal and the work function of the semiconductor. Okay. So, that's not always ideal because you would like, engineers like simpler systems, like where it doesn't matter what metal I choose, it'll still work as an ohmic junction. I won't get this weird Schottky barrier effect. I'll get an ohmic junction every time. That's what we'd like to have. But if you just choose a metal and a regular doped semiconductor, that may not happen. But if you do this instead, where you have your metal contact pad, you have your N-type semiconductor, but all you do is you add an N+ region here. Okay, what this effectively does is that this N+ region here acts like it acts like a this thing here, a tunneling type contact. Okay, so now it doesn't matter what your metal work function is. If it's such that this is the metal and N form an ohmic, great. If the metal and N++ form a Schottky barrier, it's going to form a Schottky barrier with a very narrow depletion width like this. Narrow enough so that tunneling can occur through the thin barrier. And then again, you have an ohmic contact. So it's no longer dependent on the work function of the metal, which is nice. So that is why in a lot of semiconductors, you will see that if you are trying to make an electrical contact into the semiconductor, you'll first have a highly doped semiconductor region, which can be formed by a process called diffusion. And then on top of that, you'll deposit a metal to make a connection to your circuit. Okay, so that's the tunneling type ohmic junction. This is a picture of what an actual diode looks like. I did draw this out for you one of the lectures earlier, but I thought I'd just go over it again. So this is what's called a, well, you can think about it as a substrate diode where you have a substrate contact. I guess the current would also flow laterally here, so you could also call it a lateral diode. But the names aren't not that important. It's just how the current flows is what's important. So the example below shows a p-type silicon wafer. So you started off with a p-type silicon wafer, just this p region here. And these n+ regions and the p+ regions and the n region, they can all be formed by subsequent steps of diffusion. You do one diffusion step where you form this n region, but you only form it in this portion here. Okay, you dope this region n-type and you switch the wafer. The wafer was originally p-type, but just in this area, by doping it with donors, you can switch it from p-type to n-type. Okay, then you can go through another diffusion step just in this region where you dope it with an even higher concentration of donors. And that way you can make a small n+ region within this n-type material. And then finally, like over here, you can dope this as P+, so you dope it with acceptors at a high density. Okay, and the reason for these P+ and N+ regions is because you can form tunneling type contacts. You can put metals above these P+ and N+ regions, and you don't need to worry about the work function of the metal. Because even if the work function of the metal is such that it would form a Schottky barrier, it doesn't matter because these highly doped contacts means you're going to have a tunneling type contact. And it'll still behave as an ohmic junction. Okay, so now we have all the parts of the diode. We have nice electrical contact. So this portion here behaves as a resistor. Okay, this portion here behaves as a resistor. And then everywhere where there's an interface between P and N, so I'm going to draw this in a different color, I suppose, so you can see it easier. This region here, the contact between P and N, this region here, the contact between P and N, even this out here, these areas represent the cross-sectional area of the diode. That is the interface between P and N where the depletion region forms, where all the interesting stuff happens. Okay, so if you were, for example, to forward bias this diode, I'm going to add more colors to this now. So the holes in the p-type material would diffuse this way. You're also going to have holes going up this way, like this. Okay. And then the electrons are going to be going out the other way. Okay, so the current flows through all the areas that I showed you that are circled in blue. Okay, it doesn't just flow in this region here. Let me put the laser pointer up here. It doesn't just flow at this PN interface. It flows in this entire area, okay? It's true that more of it flows here because in order for the current to get to this side, there's more resistance that it has to go through. But it's not just limited to this area, okay? So again, to sum up, the metal semiconductor contact, this acts as an ohmic contact, so it looks like a resistor, and then the current goes through this interfacial area. This interfacial area is where you have the diode-like characteristics, the depletion region. Then it gets into the N region, and then it flows out this contact, which is also another resistor. So the equivalent circuit for this is going to look like resistor, a diode, and then another resistor. Okay. This is the contact resistance on the P side, and this is the contact resistance on the N side. And this diode is due to the interfacial area. So we say the PN interfacial area. Okay. That's what a diode actually looks like. And, you know, in a single P-type wafer, you could form many, many, many diodes. All right. So to summarize, this is I would like you to just do this on your own for each combination. Choose whether the junction is ohmic or Schottky. This should be pretty easy based on the slides that we did before. So I won't bother doing that. I'll just summarize this module here. So we covered PN junctions, the standard diode. And we covered their behavior in equilibrium, in forward bias, and reverse bias. So in each of these states, we covered the energy band model. We drew energy band diagrams for them. We drew physical models, like what the carriers are doing, what the holes and electrons are doing. And when we talked about the physics, we talked about things like the carriers can do diffusion, drift, generation, and recombination. So think about the four mechanisms that we talked about from module 4 and how they apply to the diode. Also, with the electrostatics of the depletion region, we talked about the space charge region. We talked about the electric field that forms, and then we talked about the potential barrier that forms. And then we calculated the carrier concentrations at forward and reverse bias and figured out what the drift and diffusion currents are. And we derived the diode equation from that. Last class, it's not on the slide, we also talked about the transient behavior of the diode. So you should know the behavior of the diode in equilibrium, in steady state, and also a little bit about the transient behavior. And then in today's class, we talked about metal semiconductor junctions, which can either behave as a Schottky barrier diode or as an ohmic resistor, depending on what the work functions are and what the dopings are. Last time in class, we also talked about photodiodes that enable the conversion of light to photocurrents. And there's two types of photodiodes that are often used. You can use this in the photodetector setup. The photodetector setup is region 4, where you have it in reverse bias that minimizes the diode capacitance, and it makes it operate at high speeds. And then in region 1, you can operate the diode in a photovoltaic mode where it can deliver power to a circuit when light is shined upon it. All right. So I said we were going to finish early. We only finished 10 minutes early. So do we have any questions? Okay, no questions for today. All right, then. So look for today. I'm going to upload the homework solutions today for this module. There were some corrections on the homework that if anyone would like to actually stay after in class, we can kind of go over those. I know that there were a few errors on the quiz that created some confusion, so I'm happy to stay afterwards with that. And tomorrow I will send you your feedbacks on your project outlines. Okay. All right. So let me end the recording here, and then I'll stick around for questions.